Saxon Advanced Mathematics, Lesson 87. Greetings, students. It's a beautiful day. Spring is in the air, and I've got some new identities for you. Are you pumped? I know you are. If you are going to be taking the end of winter midterm with me in a couple weeks, this is the last group of new identities that will be on the test. All right, so this is the final addition I have to our list of identities. Let me explain to you first why we need them. There's a pretty simple explanation, but I want to show you. And I'm going to pull a couple. I'm just going to start with the one. The sine of 30 degrees. I can look on my nifty unit circle, 30 degrees, sine is the second value, it's 1/2, right? So you would think that if I wanted the sine of 60 degrees, you would think that I could say, oh, well, that's the sine of 30 degrees plus the sine of 30 degrees, right? You would think. I'm going to make that an equal sign with a question mark over it. Now, let's look at the sine of 60 degrees, which is also on our nifty unit circle. There's 60 degrees. Sine is the second value. It's square root of 3/2. Let me write that up here. So you would think it would stand to reason that the sine of 60 degrees, square root of 3/2, would be equal to sine of 30 degrees plus the sine of 30 degrees, 1/2 plus 1/2. It doesn't work, does it? So we cannot add identities together. We cannot add the arguments of trig identities and expect to get the right answer. It doesn't work. What we need are special identities that allow us to calculate, so that if we want the sine of 60 degrees, we have a way of taking the sine of 30 degrees and getting to the sine of 60 degrees, but it's not as easy as you think. And that, like I said, that is where these beautiful new trig identities come into play. There are 4 of them, and I'm going to list them out for you now. When you first see them, they're a little shocking. It seems like a lot, but you'll quickly see there are some nice patterns and things that make them easy to memorize. So the first thing we're going to look at is, what do you do if you want to take the sine of 2 angles and add them together, like we were doing here? That's what you have to do. You have to take the sine. This is so that if you're adding 2 angles that aren't exactly the same, right? We did 2 of the same. We'll get to that in a later lesson. But they can be different angles. Like if you wanted to add 30 and 60 to equal 90. Get this. What if you want to subtract? Just as you write this out, you can see the pattern starting to form, right? Plus, plus, minus, minus. Okay, keep that in mind. Now, what if we want to use cosine instead? Well, we've got one for adding them together. And then to find the difference between 2 cosine values. There you have them. You see the patterns. The 2 sine and the 2 cosine follow the exact same pattern of angles. They simply change out the plus and minus signs. Look here with cosine, it goes the opposite, right? If you're adding the angles, you subtract. If you're subtracting the angles, you add. With sine, positive, positive, negative, negative, okay? So you can notice all these little patterns, which I'm sure your brain did just fine as you were copying these. Memorize them, okay? And we're gonna spend the rest of the lesson looking at some examples of how this works. All right, I'm gonna turn the page. I'm sure I'll be showing you those again. As we work these problems, John recommends that we keep two other of our more familiar identities in mind. This one, we call this one the quotient function. I'm not sure why, but I mean, yeah, we divide. Tangent equals sine over cosine. And then we also want to keep our Pythagorean friends in mind. So I'm just going to write down the first of the 9, right? We know that there are 3 different types of Pythagorean identity, and we can move the pieces around to create other forms. But we're not going to worry about all that. We've got that fairly well under control. We've got that on our pages. I've got it handy. So if we need them, we'll talk about them. Okay, so how do these sum and identity creatures work in the wild? Let's look. Oh, look, I'm on the wrong lesson in my book. I want to tell you about clock problems again, but you already know. Okay, so what we want to do is it says simplify, and then we see sine, then there's big old parentheses. Okay, so we say this is a addition sign, right? It's the sign of a sum, if you will. And so we're going to use that form of the identity. It was the very first one I wrote down. And let's see. Sine A, cosine B. That's the pattern the angles take. This has the same plus or minus sign. And then we flip the letters around to do sine B, cosine A. All right. Sometimes people write this last term the other way. You can write it as cosine A, sine B, which you see are the very same trig functions and arguments, just written in the opposite order. I tend to like this one because then it's sine, cosine, and I know just flip the letters around. So I tend not to use this, but I might have written that down. Yeah, I did. I wrote it this way in the formulas. So whichever way you prefer. Okay, so this is what we're going to use. We're going to let A equal theta, and we're going to let B equal pi over 4. And that may make you feel a little uncomfortable when you first look at it. But remember, that's just an angle in radians, and we've got all of that information here on our unit circle, right? So radians strike no fear in our hearts, and I can quickly see, oh look, it's just a 45-degree angle. So I can figure that out when the time is right. What I want to do first is write out this expression with these values in it, right? So I'm going to write sine, I'm not going to use A, I'm going to use theta, cosine of pi over 4. Okay, I know I can easily find this on my unit circle. This isn't going to simplify because we don't have a number for theta yet, right? In this problem, we're just using theta as a marker. Plus, I'll use this form of it this time, the sine of theta over 4 times the cosine of A, which is plane theta. Okay, so what I can do is for the functions where I can find a value, I'm going to read that off the unit circle, and then what I'm going to do is I'm going to write that as the lead coefficient and then write the function that I can't simplify afterwards. That's just how we do it, right? We write 7x, not x7. So I'm just going to make it cute order. So let's see, what is the cosine? Oh, I already figured this out, right? No, I didn't. I just figured out the angle. Pi over 4 radians is 45 degrees. Cosine is square root of 2 over 2. Oh, and I can see right now sine is the same, right? Because 45-degree angles, that all makes sense. So I'm going to pull these two values because I know I need them both. I need cosine and sine. Pull them with my brain. Okay, so this is square root of 2 over 2, that's that, times the sine of theta, that's that, plus, this is also square root of 2 over 2, times the cosine of theta, which again, we can't simplify because we don't have the, we don't have any value for that angle, right? That's just a variable, that's just a placeholder. Theta and x are the classic placeholders for an angle we don't know. All right, so I have simplified this. There's one more thing I can do, which again is so old school, it might slip your mind. We can factor square root of 2 out of 2, square root of 2 over 2 out of both of these, and then write sine of theta plus cosine of theta. So that is the sum, if you will, of this, sine of quantity theta plus that, right? I'm not sure if you think that looks more simplified or not, but that is exactly how we use these trig identities to add trig functions. Let's do another one. How many are there in all? Let's find out. 6. Oh, we're going to change gears. Sorry. I didn't tell you that. 87.2. John says, find the cosine of 15 degrees by using a trig identity and the fact that 15 equals 60 minus 45. And here comes the magic of these sum and difference identities and why they're useful. 15 degrees is not an angle that we have on our unit circle, right? In the first quadrant where the numbers are simple, we have 30, 45, and 60. So we can't find the cosine of 15 degrees using our unit circle. But we recognize 15 is the difference between 60 and 45, right? And we have 60-degree angles. Here, I'll tip so you can see better. We have 60 degrees and we have 45 degrees. So we can find the cosine of 15 degrees using this information and the appropriate sum/difference identity. So buckle up, let's do it. So what we're gonna do is we're gonna say, all right, we can't find this, but we can find the cosine of 60 minus 45 degrees. Now, we need a formula for that, and I'm going to write it up here. So this is the cosine difference identity, right? That is on our page. It's the last one I just gave you. And this one, when we use the cosine identities, you get the cosine of both angles, and then you do the opposite sign. So in this case, we will be adding. And then you do the sine of both angles. Again, I don't think I need to point out to you the cute little patterns in these because I'm sure as you wrote them down, you noticed, oh, there's lots of similarities between these. Okay? So that means we can use this pattern to do this. Obviously, 60 is our A value, 45 is our B value. So the cosine of 60 degrees times the cosine of 45 degrees, we're going to, the opposite sign, we're going to add, I'm squishing, aren't I? The sine of 60 degrees times the sine of 45 degrees. Now, it's off to the unit circle. I need degrees on all of these numbers. Oh, I got those, okay. Equals, now we're just gonna start filling in. So I'm gonna create 4 buckets with a plus sign in between. Okay, at 60 degrees, cosine is 1/2, sine is square root of 3 over 2. Cosine of 60 degrees is 1/2, sine of 60 degrees is square root of 3 over 2. I'm just double checking to make sure I'm copying in the right place. And then at 45 degrees, those are going to be the same, right? Square root of 2 over 2 for both. All of a sudden, this looks pretty easy, doesn't it? So then we get, I just keep writing this because why not, right? Now I can multiply these. This is square root of 2 over 4 plus, that's the square root of 6 over 4. So for my final answer, I can say that the cosine of, I don't want to put it in parentheses, the cosine of 15 degrees equals that. Pretty cool, right? And with a calculator, we could quickly reduce that. Okay, of course, with a calculator, we could just we could punch in 15 cosine and get the answer for this too. But this is really nice to see that with the unit circle, we can calculate that value. Okay, let's do one more of these, and then we will change gears just a wee bit. Example 87.3. These are kind of fun, right? I just like the idea of solving a puzzle and that we can get information off the unit circle that before this lesson you might not have thought we could get. All right, simplify cosine of theta plus pi over 2. Whoa, what happened there? Looks like an elephant or a, I don't know, a llama or something. I guess my imagination's in high gear. I also passed a boy walking yesterday, a high school boy, who was wearing a yellow sweatshirt with a bright green llama silhouette on it. And I was fascinated with that shirt. I liked it very much. He also had on red shoes, which just brought the whole thing to life. Okay, I live near a high school, so when I go out walking every day with my dog, I see millions of teenagers. They're usually out and about. All right, ready? Which is nice because I don't get to see my actual students. So I see other students and pretend that they're you. Okay, so this is going to call for the cosine sum identity. That is the third one I gave you. So I'm writing it up here. With the cosine identities, I take the opposite sign. And what I do is I try to do it from memory, which obviously it would be a lot harder for you, but I know these a little bit. Every year my memory has to go and creak open the door on the vault where I store this. But I always double check and make sure I did it right. I try to do it from memory and then I double check because wouldn't that be sad to work the whole problem with the wrong identity? Oh my gosh. Okay, so again, theta is going to remain an unknown. I can't find a value for that. This I know is on my unit circle. That is, okay, if this is 180, then this is a 90-degree angle, isn't it? So we'll figure that out in just a second. Let's go ahead and write this in this pattern. Again, I can write underneath if I want A and B, just to help me. Okay, so cosine of A is theta. Cosine of B is pi over 2. I'll get that value off my unit circle in the next round. Minus sine of A, that just stays theta. Sine of B is pi over 2. Unit circle. Okay. Now I'm going to do that. I'm going to fill in these two values that I know I can pull off the unit circle, but I'm going to do the same thing I did last time where I want this, the variable, to come second. I want this, which will become a numeric coefficient, to be first. Again, we don't write x7, we write 7x. So I'm just using that same sense of logic and organization to write this. Okay, cosine of pi over 2. Pi over 2, my friends, is right here. It is 90 degrees. So again, my brain smiles because all the facts are falling into the same pattern. And cosine is 0 and sine is 1. Okay, so this is 0. That means this thing falls away. This sine is 1. Oh, yeah, 1 is the coefficient. I wrote it in the wrong order here, but I knew I was going to cross it out, so I didn't do it. Now I'm writing them like this. Right here, I just did this, because as soon as my brain saw that this was 0, I knew I'm going to cross the whole thing out anyway, so I'm not going to bother flipping it around like this. And this, that 1 can drop out, so I'm going to write my final answer, the cosine of quantity theta plus pi over 2 equals minus the sine of theta. Now there's one that really did simplify nicely, didn't it? They're full of surprises, these sum and difference identities. They reshape the original sum or difference in some interesting ways, which is useful. Okay, that is the 3 examples that worked on the sum and difference identities. Now what we're going to do is we're going to turn our attention to, and I'm going to flip the page. I want a full page to start. We're going to talk about the tangent sum and difference. And John's going to make us work for this. Now, here's the thing. John's theory, which I completely agree with, is that, yeah, we need to memorize some things, but we want to minimize what we need to memorize because memorizing is hard and it takes a long time, 10 years. It takes 10 years for information to stick in your long-term memory. Yeah, we can shove it into short-term and pull it out from time to time, but if we really want it to stick, it's going to take a while. So we don't want to memorize things that we can find in other ways. So that's the method to his madness. We're going to memorize the sum and difference identities for sine and cosine, but we're going to learn how to calculate the ones for tangent so we don't have to memorize those as well. So for 87.4, John encourages us to develop an identity. Develop means you don't have to memorize it, try to work it out. For a tangent sum identity. All right, so what we know is that tangent equals sine over cosine, right? And we talked about that at the beginning of the lesson. I said John wanted to put it in our heads. Here, I'll show you on a different page. John wanted to remind us that tangent equals sine over cosine. So this is the identity that we're pulling out of our memory. But instead of having it be a single argument, we're going to use this sum as our argument. And what's cool is this will be true. Okay, so now what we can do, we have an identity for this, we have an identity for that. So we're going to plug those monsters in to this fraction format and then see what we can simplify. So pretend I'm going in a line, but I'm going to start over here, right? So I'm going back over here. The sine of a sum is plus that, and then the cosine sum identity it's got the mix. Oh no, this is wrong. This is cosine B. and then we subtract, right? I was so busy thinking about the sign being different, I messed up the functions. Just double checking my work to make sure I did not go off the rails. Okay, beautiful. Now, what we can do is we can separate these into two separate fractions. And then it will be wait a minute. What I'm doing, don't do that. What I'm doing is I'm rewriting this fraction, these four pieces, so that I can put denominators under them. Check this out. Sine A cosine B plus sine B cosine A, and then it's over this, right? Then we have the big fraction line, right? That this is this, and then we have cosine A cosine B minus sine A sine B. So what I did was I took this fraction and I just rewrote it. Ignore this. I rewrote it so that each of these has space underneath them, because I'm going to come back and give each one of our original four pieces a denominator. Now, how do I choose what that denominator should be? Well, I always look here, okay? This is where I start. And what I want to do is I want to set this denominator to 1, the lower left. I'm going to write down this in a second. But I go to the bottom left of the fraction and I take whatever's in the numerator of that corner and I create the same denominator. Cosine A cosine B. Okay? So, okay, so I set the lower left term's denominator to equal 1. For reasons I can't explain, for lack of a better place, we always start here, right? These are my four different pieces. I start with the lower left. I set that one equal to 1. So this expression drives what I'm going to do next. Then what I do is give the same denominator to all four others. So I'll go this way first. Cosine A, cosine B. Laws of algebra, right? It all has to be the same. And my second instruction to this is all others must follow that setting the lower left, right? Now, look what happens. We've got things that are going to cancel. A pair of cosine A's, right? This completely cancels, right? All of these are going to drop out. I'm circling what we'll be able to cancel. And then this stays the way it is, right? Now, notice that when they cancel, let's look at what's left. I'm going to use a different color for that. What we have left behind here, sine A over cosine of A, has become tangent of A. What's left over here, sine B over cosine of B, has become, I'll squeeze it in down here, tangent of B. This turned into a big fat 1. And here, look, we've got tangent of A and tangent of B. And we're multiplying them. Do you see what I'm saying? Red is where we multiply. Then I circled in red what will cancel. Let's do this too. Let's cancel these out. That cancels, and these cancel. These all cancel, and these don't cancel at all. So now what we have left is what's in blue, right? Sine over cosine of A gives me tangent. Sine of B over cosine of B gives me tangent. This all dropped to 1, which was exactly what we wanted. And then this one, I've got 2 tangents that can multiply. So what I'm going to do is I'm going to copy the blue part to the next page. And I get that we had tangent of A plus the tangent of B over 1 minus the tangent of that. They multiplied together in that last one. This is our answer, and now this is an identity that we can use on tangent identity problems. We don't have to memorize it, although it helps if you see it when it jumps up in your face, right? So that you're like, oh yeah, that's right. Now we can use it in an actual problem, and that's what our next step is. No, that's not true. Well, let's skip to 87.6. Whoops. 80. We're going to skip over 5 and come back to it because 87.6 says use this in an actual problem. It says evaluate the tangent of theta plus 45 degrees. Now, we've already got that identity ready and waiting for us because we just worked it through, right? So we can let this equal A and this equal B, and we can use this to factor. So it'll be the tangent of theta plus the tangent of 45 degrees. That we can pull off our unit circle in a few minutes over 1 minus the tangent of theta times the tangent of B, which is 45 degrees. Oh, all right. Now to do this, we're going to need the tangent of 45 degrees, right? And we can get that from our unit circle, but we do have to calculate. At 45 degrees, what we're going to do is we're going to remember that the tangent of 45 degrees equals the sine of 45 degrees over the cosine of 45 degrees. We're working around the fact that we don't have tangent on our unit circle, do we? We just have cosine and sine. At 45 degrees, they are the same, right? Cosine and sine. So we can plug those into this. Square root of 2 over 2, square root of 2 over 2. That makes perfect sense because we know at 45 degrees, sine and cosine should be the same, so that's nice. So that brings us to the startling fact that the tangent of 45 degrees equals 1. Oh, okay. So now we can take this lovely detail and plug it in up here. And what we will get is, I'm just going to cross this out and write 1. And so our final answer, I'm going to have to flip to the other page. That is so unsatisfying when I have to flip. The tangent of theta plus 45 degrees equals tangent of theta plus 1 over 1 minus the tangent of theta. And let's just check and make sure. Tangent of theta plus 1 over 1 minus tangent of theta, because that turned to a 1 also. Beautiful. That's our final answer. Again, we can't simplify tangent of theta because that's just a placeholder, right? That's like saying tangent of x. So this is the most simplification we can do. Yay! So we take advantage of the fact that tangent equals sine over cosine. We take advantage of the fact that we can use these sum and difference identities in the same way that we can combine otherwise. And then we can use this to simplify tangent identities. Whoa, it's kind of trippy, right? Our last problem is to develop an identity for tangent of a minus b. And that's why I did the other problem first, is because that was an a plus b identity. So I wanted to do the specific problem with that before we change gears and start talking about the difference. All right, I use my same starting point. The tangent of a minus b is sine over cosine. I do have identities for both of these, so I'm going to use the whole row to write them out. Sine of a minus b is this one. Of course, you can check your notes to find out. I've got it listed right here. Sine of a minus b is sine a cosine b. Oh, this should be a minus. Gotta always be vigilant, right? Sine b cosine a, beautiful. That's the numerator. Now this time, because we know what's coming, I'm gonna make space for my new denominators that I know I'm gonna need. And then I'm gonna write this identity in the bottom part. And this is cosine a cosine b, and this is the one where we use the same, the opposite sign. Sine, we use a matching plus or minus. Cosine, we use the opposite plus or minus. Sine a, sine b, and then we know that we're going to make those both into fraction as well. How do we know what to put in the denominators of all of these? Lower left. We use whatever expression is in the lower left to simplify. So we're going to use cosine A, cosine B. That's how we know. I put a star there to remind you that that's the starting place. That's how we know which denominator or which expression we want to use as our new denominator. And then I go all around the group, giving everyone the same denominator. And getting excited because there is going to be a cancel party in just a minute. Okay, this cancels. This is the awkward one to cancel because they're not above and below each other. This cancels. And nothing, both cancel here, nothing cancels there. Okay, so that's the pattern you'll always see. One set cancel, one set cancel. Everything cancels, nothing cancels. But now let's go through with our other color and circle where we now have tangents. That's a tangent. That's a tangent. This is just a 1. And this is a pair of tangents. So we once again are going to rewrite this. Tangent of quantity a minus b equals, and then this will be tangent, tangent, 1, tangent, tangent. All right? So, yikes. My book took on a life of its own. Equals The first one is the tangent of A minus the tangent of B over one plus the tangent of A times the tangent of B. And I'm just double checking. There are a lot of subtle details to this, and making sure we get the signs right is a big part of it. A minus B, 1 plus. Okay, beautiful. Now, this is correct. Now we've developed both, right? We've done the tangent difference and we did the tangent sum a few minutes ago. What I'm gonna do is I'm gonna rewrite the tangent sum identity right here so you can see them together. Here's this one. I want you to see how similar they are. The actual terms are all the same, right? Tangent of A, tangent of B, 1, tangent A times tangent B, there. What's different and what's important for you to always stay vigilant about is the plus minus signs. So easy to make a little mistake and destroy these, okay? So the top plus or minus sign matches to what's in the original quantity. The bottom plus or minus sign should be different, okay? So as we're going through these trig identities, but really all of them, pay attention to those subtle little patterns that we see that make it easier, maybe not to memorize, because again, I'm not asking you to memorize these, I'm asking you to know how to calculate them as we just did. But what's really important is that you know what to look for, you know what the patterns should look like, and you know where to be careful. And the plus and minus signs are where I definitely want you to be careful. All right, this is a new way to use identities, to develop them from each other. And that's something that we're going to be working on as we go forward. You now have a lot of the building blocks, right? All these identities that we have been working on. We're going to use these, as we did today, we're using them in combination to build new ones that we don't have to memorize. That's why memorizing these original ones is such a good idea, because you're going to be using them for a long, long time. Happy days! Guess what? That's the end of lesson 87. As I said, if you're taking the midterm with me at the end of March, that's the end. That's the end of the ones you have to memorize. This sheet that I've been showing you that has all the identities on it, I'm going to attach a copy of this to your test. See, it says winter midterm identity page. Obviously, the green is what I filled in, and that will be your job on the test to fill in the same. If you do not normally take tests with me, but you would like a copy of this sheet, I can send you a PDF. Just reach out to me in the email if you would like that. Okay. Yay. Thank you. Goodbye.